Hello and welcome back. So in 1.5, we'll take a look at a review on exponential functions. So the basic format, f of x is b to the x. Usual rules for exponential functions, b is not worth 1, otherwise 1 to any power, you're still just at a constant function, and that would just be of the form f of x equals c. And here b is also going to be greater than 0. As far as the domain, though, domain we can put in any real number we want. So set of all x such that x is in the set of reals. Our range, 0 to infinity. So take a positive base, raise it to a power, you're going to get a positive result. A quick little exercise for you. Try out different values of x for the expression 1 plus 1 over x raised to the x. So try out x equals 1, and then just keep growing at x equals, let's say 500, and then try 500,000. And you should notice you're getting close to a certain constant. So go ahead and try that out. Pause the video if you need to. Okay, welcome back. So hopefully you saw that even as you're starting to plug in bigger and bigger numbers, the output isn't growing forever. The output is actually approaching a limit, a constant value of about, sorry, not x is approximately equal to it. As x goes to infinity, this expression ends up being about 2.718281, keeps going and going and going. This is e. So that's a special number in calculus. We'll see a lot of that number coming up this semester. So growth and decay models use e. The new amount is the initial amount. Times e to the k times t. K is the growth or decay rate. K positive, it's growth rate. K negative, it's a decay rate. So this is something that is used in populations. So let's say we have a town, 5,000 people. Growth rate of 4%. So 0.04. And we'll look at the population in 5 years. So the new amount, the population after 5 years, is the initial amount, 5,000 people at t equals 0, times e to the rate of growth, in this case 0.04, times t equals 5 in years. So a is approximately, and we'll round to the nearest person, 6,107. So see if you can give it a try. Same problem, but at 10 years and 15 years. So go ahead and pause it, find the 2 other population numbers. Okay, welcome back. So at 10 years, the new amount, initial amount of 5,000 people, e to the 0.04, but instead of times 5, times 10, and similar setup for the 15 years. Initial population times e to the growth or decay rate times the amount of time. And we're at about 7,459 folks in 10 years, and we're at about 9,111 folks in 15 years. So one thing you might notice is that the rate of change is changing on this. We have a variable rate of change. We have a change of about 1,100 people from getting to the from 5,000 to the 6,000, about 1,100 difference there, about 1,300 difference from 5 years to 10 years, and about 1,600 difference from 10 years to 15 years. So the growth rate is accelerating in this exponential function, even though the increments of time were changing by the same amount: 0 years, 5 years, 10 years, 15 years. Decay works in much the same way, except instead of a positive, it's negative. So carbon-14, carbon dating, you've likely heard of that. It decays at a steady, predictable rate. So it's used to sort of figure out the rough age of various objects. I'm not going to have you memorize the number on it. It'll just be given. Triple 0, 1, 2, 4, T. I'm just spacing these out a little just to make it a little easier to read. So A naught here is the amount of carbon-14 at the time of death. So this is used on living objects. So for example, if we had 1,000 milligrams of C14 at time of death, how many milligrams C14 after? We'll start with a decade. So our initial amount, 1,000, times e to the negative 0.000124. Decade would be 10 in years. And then we plug and chug that on the calculator, and there should be about 998.76 milligrams of C14 after a decade. So see if you can try after a century and a millennium. Missing a letter there. So 100 years, 1,000 years. Okay, welcome back. So amount 1,000, e to the negative 0.000124 by 100. That should give you about 987.68 in milligrams, and 1,000 e to the negative 0.000124 times 1,000. About 883.38 also in milligrams of carbon-14. So if we know that whatever living organism, plant or whatever, had 1,000 milligrams of carbon-14 in it at the time of death based on the size of the object, and we measure it and we find 883 milligrams of it left, we think that it's about 1,000 years old. So not only population models and scientific models use this, in banking, we also would use this in continuously compounded interest. So the idea is still the same. New amount is initial amount. You'll either see P or you'll see the A0 that we used before times e to the either K or R times T. But either way, K or R, we're talking about the interest rate. So let's say that we deposit, let's say $400, and it is continuously compounded for, let's leave it in there for 10 years. So let's go with 1.05% compounded continuously. So our closing balance, that's what we're looking for. The new amount, initial amount, we dropped in 400 and just parked it there for a decade. E to the 1.05, it's in percent, so we need to turn it into decimal form. So slide that decimal over twice. And for money, we would just typically round it to the nearest hundredth. Banks would more commonly do what they call truncating. So even if the next number is a 9, after this 8, they would give you the 28 cents, not the 29 cents. They never would round up. So after 10 years, we'll have, and that would be in dollars, so $444.28. So one more thing that we can do with these, we can also graph them. We can just make a quick little easy table with fractions. So we'll sketch. We'll do y equals 2 to the x. We'll start with that one. So we'll plug in values from -3 to 3. So y equals 2 to the x, so y equals 2 to the -3rd, which is 1 over 2 to the 3rd, so that is 1/8. Y equals 2 to the -2nd, 1 over 2 squared. So negative exponents, remember, we flip them into the denominator, and they kick over to positive. Any non-zero number to the 0 power, always a nice, neat, pretty 1. 2 to the 1st, it's just a 2. 2 squared, of course, a 4, and 2 cubed. It's an 8. I have my handy dandy stamper here, so we'll just kind of use the paper as a guide here. So then each line here, each line would be 2, so every half. And It's kind of a quick, easy way to get yourself a little makeshift graph that's reasonably accurate fairly quickly. So 2 to the 0 is 1, 2 to the first is 2, 2 squared is 4, 2 cubed is 8, 2, 4, 6, and 8. And then we have 1/2, 1/4, 1/8. We're getting closer and closer to the axis without touching it. So we do have a horizontal asymptote. You remember those from your college algebra days. So think of what would change if we had 2 to the opposite of x. Well, what happened at -3 is now what happens at +3, and vice versa. What happened at +2 now happens at -2, and so on. So our table we can make pretty quickly without really much need for heavy-duty calculations. So the -3 has the 8, the -2 has the 4, -1 has the 2, 0 power is still a 1, 2 to the -1st is a half, 2 to the -2nd is a fourth, 2 to the -3rd is an eighth. So we just have this flipped around, and that should make sense. Your y, excuse me, your x values reflected. So we changed x for its opposite. We flipped it across then the y-axis. So now -3 is our +8, -2 is our +4, -1 is our +2. Any non-zero number, the 0 power is 1. So we're just heading, again, towards that same asymptote, but in the other direction. So we still have y = 0 as a horizontal asymptote. We just don't have it in the same direction. One thing that you might notice that is also the same as if I had asked you to graph y = 1/2 to the x power. Well, 1/2 is 2 to the -1st. Power to a power, we multiply. So 1/2 to the x and 2 to the -x would look exactly the same. All right, so some problems to try out. This was from 1.5. Don't forget we covered 1.4 as well. 1 to 10, I would try all of those. 29 to 41 on the odds. And then 51, 53, 63, and 68 are all some interesting word problems. If you have any questions, please get in touch. Otherwise, I'll see you next time. Stay safe out there.